Example 2.1.3, in the figure provided, the vertical scale represents 5 volts per division. All waves have a 0 volt offset. Determine the RMS and peak voltage value for each. So the givens here, it's all given in that figure, so I'm not just going to redraw it. So no point really in this step for this particular solution. We're asked to find the peak value and the RMS value for both that square wave and the sine wave. The solution. Well, first we have to interpret some of this information and apply it to the graphs. The first is that the vertical scale represents 5 volts per division. Vertical is up and down, horizontal is left to right. Hopefully you know that by now. But what that is saying is that distance from there to there is 5 volts. We also call that the, well, we can see that on this symbol, this drawing, that's also the peak voltage right there. The 0 volt offset is telling us that the average value of the waveform is 0 volts, which means that that line right there represents 0 volts. If there's no offset for a square wave, then we know that the average value over one cycle has to be equal to 0 volts. So there's as much area up here as there is down here if that's the 0 volt setting. So that also allows us to determine what the peak value for the square waveform is. It's also 5 volts. So just by inspection, we've been able to determine that the peak value for the sine wave equals 5 volts, and the peak value for the square wave is also equal to 5 volts. So we're going to go ahead and determine the RMS value for the sine wave next, V RMS. In the notes, we found that the RMS value is just equal to V peak over root 2, and that's a lot of times that's written as 0.707 times V peak, and so that's going to be 5 over root 2 is 3.54 volts. So that's the RMS value for the sine wave. We didn't in lecture come up with a handy-dandy formula for the RMS value of the square wave, so we're going to have to start with the definition of the RMS function. And for any wave shape, the RMS is given as the root of, so root of the mean, and we take a mean of a function by using calculus. We integrate over one period. That's what this means, integrate over one period. So we divide that by the period to get the mean. And then finally, the s is of the square of the function. Well, I should maybe write that as v of t since we're talking about voltages here. And since it's calculus, we need to integrate with respect to t. So we need to figure out what this v of t function is for this guy right here. So I'm going to just write that. V of t, this is a piecewise linear function. We see that one formula defines the voltage in the from 0 to t over 2, and another function defines the voltage from t over 2 to t. So I'm going to say v of t is equal to v max, or it's equal to negative Vmax. Those are the only two values it can take, Vmax here and minus Vmax here. And this is for 0 is less than or equal to t is less than or equal to t over 2, right? That's halfway because it's a 50% duty cycle square wave. And it's negative Vmax for t over 2 is less than or equal to t is less than or equal to capital T, the period. So that's our function right there. We need to substitute this function v of t into the RMS value right there. So it's we would say these piecewise linear statements are going to affect our limits when we insert the function right there. Remember, we also have to square it. So VRMS is going to be equal to root of 1 over t, and first I'm going to go from the integral from t0 to t0 plus t over 2. Oh, yep, so that's the first half here. And that's v of t squared over those limits. So that's v max squared. And then I put my dt there. Now I have to go from t over 2 to t. So that's the integral from t0 plus t over 2 just to t0 plus t. So that's this here. And that's going to be of minus v max squared dt. So you can see that minus Vmax squared is going to be the same as Vmax squared. So in this case, this really simplifies down to 1 over t integral from t0 to t0 plus t of Vmax squared dt. So that's pretty nice. Okay, so if we want to perform that integration, we'll notice that Vmax is not a function of t, so it can get pulled outside of the integration operator. So we get the root of 1 over t times Vmax quantity squared integral from t0 to t0 plus t of dt. Integrals don't get too much easier than that. That's just going to result in the square root of 1 over t Vmax squared. I just have to take t and evaluate it from t0 to t0 plus t. Right? The integral of dt is just t. And then since I have limits, I need to take a definite integral right there. So I can evaluate this. This is the root of Vmax quantity squared over t times the upper limit of integration minus the lower limit of integration, t0 plus t minus t0. And so that simplifies down to the root of Vmax squared over t, just times the period. These cancel. We get the root of Vmax squared, which is just equal to the peak voltage right there. So if we scroll back up, we see that the RMS voltage for this square wave is equal to the peak voltage, 5 volts. VRMS is 5 volts for that.